of this course starts with Dr. Nandini Gupta, ma'am. The topic of the second day is entirely about partial discharge, and the first talk will be about an overview of partial discharge, and it will be delivered by Dr. Nandini Gupta, ma'am. So Nandini Gupta, ma'am, obtained the PhD degree from Indian Institute of Technology in 1998. She was a
No. Indian Institute of Science.
Sorry. Yeah, of course. IISc Bangalore in 1998. She was a postdoctoral researcher at the University of Windsor, Canada, and Eindhoven University of Technology, the Netherlands. She is currently an assistant professor in the Indian Institute of Technology, Kanpur, India. She works in the area of dielectrics and insulating materials, partial discharge, and treating, and application of plasma discharge.
You've taken my bio from a very old website.
Yeah. Okay, sorry, ma'am.
That's okay.
So,
done?
Yeah.
Okay. Good morning, everyone. Today I'll be talking about partial discharges, and I'll try to give you a theoretical overview of what partial discharges mean and what measurement of partial discharges encompass. Give me a moment to share my screen. Okay, so what are partial discharges? Now, when we talk about partial discharges, the first thing that we need to talk about is what is breakdown. Yesterday, there was a question, what is the difference between breakdown and surface flashover? A more pertinent question would be, what is the difference between partial discharges and breakdown? So when you have two conducting electrodes, and you have a dielectric in between, for example, in the case of a capacitor, when you exceed a particular electric field, and please be careful, this is not a voltage that we are talking about, but we are talking about electric field, which is the rate of change of voltage with space. It is not voltage, but space. So when within the dielectric, the electric field exceeds a certain critical value, that critical value, of course, is dependent on the material, as Asha pointed out in yesterday's session. It is the breakdown strength of the material. So when you exceed the breakdown strength of the material, the insulating material ceases to be a dielectric, ceases to behave like a dielectric, which means that it is no longer able to withstand charge flow through it, and it allows current to flow through it. It becomes conducting. This is breakdown. However, when we are talking about partial discharges, we are not talking about a situation where the dielectric loses its insulating property entirely. Instead, what you have is, in a small region near one of the electrodes, or maybe not near any of the electrodes, somewhere within the dielectric volume, you will have localized electric field enhancement. Let me tell you what I mean by that. Here I have a simulation where I have a needle plate geometry. Somebody talked about the radius, so you see this has a finite radius. And what you can see here is that the colored regions indicate the fields in these regions. So everywhere, let's imagine that this is air. So everywhere within the dielectric volume, you have quite low values, which is indicated by this blue region. But as you reach near the needle point, you see that the field gets higher. The yellow region has a high field, and the highest fields are in this red region, which is right next to the needle tip. So there might be a situation where this blue region may be something like 10 kV per millimeter, which is well below the breakdown strength of air. And that's fine. We don't have a problem here. But even when you have tolerably low values within the dielectric volume, there might be a very small region in this red region, let's say, where the field is 50 kV per millimeter, which means that In this small region, there has been local field enhancement, and this field enhancement is much higher. Kinshuk, you need to mute.
Asha ma'am, you have
Kinshuk, you need to mute.
unmute.
So in this region,
Asha ma'am, please unmute.
Kinshuk, you are not muted.
Ma'am, Asha ma'am is not.
Oh, okay. Yeah. So in this region, you have very high electric fields. And in this small region, the electric field is higher than the dielectric breakdown strength of the material in question. What would happen then? The air, the gas within the small region would tend to ionize, and there would be current flow. Ionize, so charges will be created, and when charges are created, these charges move around. Movement of charges is nothing but electric current. So what you have is, you have partial breakdown of the insulating medium in a small region of localized high electric stress, and that is partial discharge. The dielectric medium does not lose its insulating property, so there is no complete bridging of no complete path to bridge the path between the electrodes. You don't have a direct path from high voltage electrode to the low voltage electrode, but you have ionization of a very small region. Many of you, even if you're not familiar with partial discharges, will be familiar with corona. And one question that I would like to put to you is, what is the difference between corona and partial discharges? There is actually no difference between corona and partial discharges. Any partial discharge that happens in the open air is termed as corona. So generally, when we see partial discharges happening around transmission lines, we call it corona, but there is essentially theoretically no difference between partial discharges and corona. Partial discharges are generally the breakdown, the partial discharges that happen inside a solid dielectric material are termed PD, and when it happens in open air, it is called corona. What would be the reason for such localization of electrical stress? In a solid dielectric, there would be many reasons. There can be voids which are incorporated in the insulation during manufacturing. There can be delamination at insulation interfaces. So when you have an electrode, a metal electrode and a dielectric placed side by side, they are laminated so that any air gap between them is eliminated. If that does not happen, I would like to mention that when you have two layers of dielectric side by side and they have different permittivities, I'm not going to work it for you here, but the material with lower permittivity will be very highly stressed. It will be more highly stressed because of the presence of the high permittivity material than if it was there alone. So whenever you have a solid dielectric with high permittivity or high dielectric constant, and if there is a small gap, the gap would be stressed much more if there was no solid insulating. So essentially, the presence of a high permittivity material in the vicinity of a low permittivity material tends to exacerbate the electric field in the low permittivity material. So delamination at insulation interfaces, either with the electrode or between two insulating layers. Remember, in practical situations, we don't always work with just a single insulation. We might have layers of insulation, we might have mica epoxy, we might have oil paper, etc. Delamination at insulation interfaces can be a reason for local field enhancement. There might be mechanical defects, which might be there from the outset or might happen due to whatever reasons. Treeing, I'll come to treeing later, what treeing entails. There might be any other manufacturing defects. So there will always be something beyond our control in the insulating medium, in the solid insulating material, which can cause local field enhancement. And when that happens, there is always the probability of partial discharge happening. Partial discharge, it is not necessary that it will definitely happen, but it can happen. And that is why we have to be careful about partial discharges. What I'm going to do now is I'm going to try and explain how partial discharges happen and try to give you some insight about the nature of partial discharges. with some theoretical assumptions. Here, what I do is, let us say this is my electrodes, metallic electrodes, and I have a solid dielectric volume in between. It can be any material. Let us imagine that there is a void in this material. For convenience, I have taken this void to be rectangular in shape. It is not necessary that it be rectangular in shape. So I have a thickness of D, which is the void thickness. In series with the void, I have the solid material, which is unperturbed, which is perfect, of D1 thickness and D2 thickness on this side. Now, as I keep on increasing the voltage across the entire solid dielectric material, the voltage across the voids will also increase. And there will come a time when the voltage that appears across the void divided by D, which is the electric field that the void will experience, will exceed the dielectric strength of air or any gas which is present in the material. And as things go, the dielectric strength of this gas will definitely be lower than the dielectric strength of the solid material in series with it. So well before the solid material reaches anywhere near its breakdown strength, the material in the void, the gas in the void, might exceed the breakdown strength of whatever gas or air we have. In that situation, this material is going to break down. So there will be a breakdown of the void. What does breakdown of the void means? What I mean is, when you apply an electric field, there would be charge which would be deposited on the capacitor plate on the top, let's say, and at the bottom. At the same time, due to leakage current, there would be some charges which will flow through the solid dielectric material and will reach the void interface, the dielectric void interface, and there would be charges which will be deposited here. So there will be charges on the void top surface of the void, there would be charges on the bottom surface of the void, and there would be, in an ideal situation, no charges flowing in the void till breakdown happens. When the void breaks down, these charges will flow through the void and they will recombine each other, so the void will no longer be able to hold a voltage across it, and the voltage across the void will go to zero at the instant of breakdown. And the charge that was originally on the top and bottom of the electrode will recombine and will be removed. So this is what happens in the process of partial discharge. So if you try to build an equivalent circuit for this void, what you would have is, you would have the capacitance of the void till the void breaks down. You would have the capacitance of the void. You would have a capacitance of the material which is in series of the void. Of course, you have material which is on top of the void as well as at the bottom of the void. Let's just lump them together and consider them as CS. So CS is the total capacitance of the solid dielectric material which is in series of the void, be it on the top, be it at the bottom. In addition, you would have a capacitance of the rest of the dielectric material, which is voidless, which is in parallel with the void. So this is, of course, an idealized scenario where you have a dielectric material and you have a single nice void. Now, till the void discharges, you have charge being deposited on the top and bottom of the void. And at the instant that the dielectric strength of the void material, which is air or some other gas, is reached, the void breaks down. When the void breaks down, a certain quantity of charge is removed from the void and they will be recombined, and therefore they are lost. Let us imagine that this amount of charge which is involved in the discharge is delta Q. As long as the void does not break down, this charge which is present at the top and the bottom of the void results in a voltage delta V across the void. The moment this delta Q charge is lost, this delta V is also lost and the voltage across the void becomes zero. Let us imagine that delta Q is the charge which results in a voltage difference of delta V. And then we should be able to write an expression for delta Q in terms of delta V and the capacitances in series with the void and the capacitance of the void. What is delta V? Delta V is the voltage VB. If VB is the voltage that is required across the void to cause discharge, so VB is the voltage across the void at the instant of void discharge, and VR. Now, I have just said that once discharge happens, the voltage across the void goes to zero. This is an ideal situation when all the charge that is there in the void on the surfaces of the void is dissipated. This may not always be true. The dielectric may be able to hold some amount of charge, and therefore, even after discharge, you might find that there is some residual voltage across the void. Let us call that VR. So therefore, the delta V that you have, because of the dissipation of a charge delta Q, is equal to VB minus VR. What happens to this delta Q? This delta Q results in a discharge, and when a discharge happens, what essentially happens is that charge moves. Movement of charge is nothing but current. So whenever you have current, you have I square R losses. So there would be heating. I mean, it is not necessary that you would just have heating. I'll come to that later. But what essentially will happen is that whatever discharge, as this charge is dissipated, there is a partial discharge, and that partial discharge will dissipate energy. The amount of energy that is dissipated in this partial discharge within the void can be estimated as delta W, which is equal to approximately half CV delta V square. So again, the discharge energy is related to the voltage difference across the void before and after discharge. So this is what we understand about the process of discharge. So we apply voltage across the material. It results in a voltage across the void. At a certain point, the voltage is too high for the gas within the void to be able to withstand it. And therefore, there is a discharge within the void. As a result of discharge within the void, the voltage within the void falls to zero or some very small value, and the charge across the void is dissipated in a discharge and results in some quantity of discharge energy. I think this is clear. Let's go forward from here. If any of you have worked with partial discharges, you're aware that PD are pulsative quantities. When you apply, when you're trying to measure a PD in the laboratory, as you will see in this afternoon, what you essentially see are some PD pulses. Why is PD pulsative in nature? Let me try and explain that. Let us imagine that I apply a certain voltage across the dielectric. So I'm talking about the voltage that is applied across the metallic electrodes. This will result in a voltage across the void. In this particular slide, I'm calling that voltage EA. So EA is the voltage. This is not electric field. EA is the voltage that appears across the void because of voltage that is applied across the metallic electrodes. If this is an AC voltage, as the voltage increases, at some point, let us imagine that when the voltage across the metallic electrodes reaches its peak value, the voltage across the void also reaches a peak value, which is of course smaller than the applied voltage across the metallic electrodes. And let us imagine that that peak value EA is equal to EB, which is the voltage required for the gas within the void to break down. This is an assumption I'm making in this particular case to try and explain something. So if EA is equal to EB, as the voltage across the void rises, you don't have a problem. The voltage across the void is increasing. The voltage across the void reaches EA. At this point, EA is equal to EB. And if you assume that this is an ideal scenario, at that particular instant, now, of course, we know that if the dielectric strength of air is 30 kV per centimeter, it is not necessary that as soon as 30 kV per centimeter is reached, air is going to break down, because breakdown is a stochastic process, as Asha explained to you yesterday. But let us imagine that that happens. For the sake of understanding, let us imagine that as soon as EA is equal to EB, the void breaks down. So at the very instant that the void breaks down, the voltage goes down to zero. Again, I'm assuming that VR is equal to zero. There is no residual voltage after breakdown happens. This is just for the sake of understanding. Now, once the voltage reaches 0 across the void, remember, the dielectric has not lost its dielectric property, insulating property, and therefore you are still able to apply voltage across the metallic electrodes. So as the voltage across the metallic electrodes continues to follow the sine wave, the voltage across the gap will also continue to follow the sine wave. But at the instant that the voltage across the void reached EA, the voltage was brought down to 0. So as the applied voltage across the void diminishes from EA to 0, the voltage across the void will also follow the same wave shape, but in this case, it will fall from 0 by the same amount EB or EA, and therefore its voltage will now become minus EA. Now, if EA is equal to EB, and let us also imagine that the positive and negative voltage breakdown voltages are the same. So as soon as it reaches minus EA, it will again break down, and again the voltage will go to 0. At this instant, the applied voltage across the void is also 0. So as the voltage now increases in the negative direction, the void voltage also increases in the negative direction, goes to minus EA when it breaks down again. And then during the last half cycle, it follows the applied voltage and goes from 0 to plus EA, at which time again, at which instant it again breaks down. So what I see is within one full cycle, we find 4 PD pulses. I'm not going to go on and describe all the cases. Now, if you consider the case where you have EA is equal to 2 EB, you can follow this diagram and you can see that you will have 8 PD pulses. So what this explains is that because of this particular phenomenon, you can explain the pulsative nature of PD, and the number of pulses that you would have for in every cycle depends upon the ratio of the peak voltage of the applied voltage and the breakdown voltage that is required across the void. Remember, in all these discussions, I'm talking in terms of voltage. Each voltage will correspond to a corresponding strength, which you can figure out. So PD is pulsative in nature, and the number of pulses that you would have would depend upon the ratio between the EA and EB. But remember, we are talking about huge quantities of solid insulation, and there may be a very small void somewhere in between. So essentially, the EA and the EB ratio would generally be very, very high. So you will not end up with 4 pulses or 8 pulses. You will end up with a very large number of pulses for every cycle. So when you apply voltages, you don't see 1 pulse, you don't see 2 pulses. You actually see when PD is steady and you have lots of activities going on, you will be able to see a very large number of PD pulses in every cycle, and they will keep repeating in every cycle. I'll come to that later. So this is about the physics of PD, why PD happens and why PD has a pulsative nature. You're also aware that in current scenario, we are concerned with condition monitoring of insulation because we are working in a competitive environment. Reliability is important, and we cannot really wait for things to happen, wait things to fail before we take corrective action. And in terms of condition monitoring of power equipment, it is very important to condition monitor the insulation, because very often power apparatus fail because insulation fails. And if you are anyway familiar with condition monitoring, you will also be aware that PD monitoring forms a very important part of condition monitoring. And why is that? Partial discharges have a two-pronged role to play in dielectric materials. Firstly, it is a symptom of degradation in the insulating system. So what we often do is we have a new machine and PD monitoring is done, and over time you would continue to perform PD monitoring so that when you see a change in the PD patterns, I'll come to what I mean by PD patterns a little later. When you see a change in PD patterns, you might become aware that something might be amiss. So if you have PD, it probably means that there is something going on in the insulating material, and that is causing degradation. So you need to take action. You need to use that as a symptom of degradation, and you need to decide whether this needs corrective action or not. So in this sense, PD is a diagnostic tool. But apart from that, we need to remember that PD is also a stress mechanism in itself. So if you have a PD, it might be because something is wrong somewhere, but apart from that, if you start having PD, PD is going to turn into a problem on its own. To give you an analogy, for example, when we have fever, when a human being has fever, when a person has fever, the fever is an indication that something is wrong. So you might not really be facing too much problem. Like, for example, when you have COVID, very often people just have 99 degrees of fever and it's not a problem. You can go around. But it is symptomatic of something much more serious. And therefore, you would like to take action. You would like to go to the doctor. You would like to do a test and figure out whether it is a fever that is from a cold, in which case you can just go home and sleep it off. Or if it is a fever due to COVID or something very serious, in which case action might be necessary. So that is one way. So as a diagnostic tool, fever is similar to PD monitoring. If you have PD, if you see PD happening, you might want to take action. But remember, in case of fever, suppose you have very high fever. Let's say your fever goes up to 105 degrees. At that point, you don't really bother about what is causing the fever, but you try to bring down the fever itself. Because if you have very high temperatures, if your temperature goes beyond 105 degrees, your brain might be damaged. So in that case, you're going to worry about the doctor later, and you're going to first try and figure out how to bring down the fever. So we have the same situation. Okay, PD is a diagnostic tool, but if you have a large amount of PD, you want to figure out what is causing the PD, and you might want to stop that right away before something catastrophic happens. So PD can behave as a damaging mechanism in the further deterioration of the insulation. And if PD happens, you already know something is wrong, and you might also want to take action. When I say that partial discharges are a stress mechanism in itself, what are the stress mechanisms that PD can be responsible for? Now, there are various kinds of stress mechanisms that can be related to PD. So the thing that I said is, when you have a partial discharge, what happens is you have dissipation of energy. What is the kind of energy that PD dissipates as? When you look at corona, you have some idea about what are the dissipation mechanisms, what are the various kinds of energy in which partial discharge can dissipate. When you see corona, as soon as I say you see corona, it means that you can see it. You can see corona because there is light emission, which means that energy is dissipated as light energy. You also hear corona, there is a hissing sound, which means there is dissipation of sound energy. You can also smell corona because corona gives rise to ozone. When we are talking about partial discharges within a void, it need not be just ozone. There can be various other chemical reactions happening. So basically, all the various ways in which the energy in the partial discharge is dissipated would also result in stresses. And again, I'll come to this later, would also give us means to be able to detect PD. So the stress mechanisms that we see in PD are particle impacts, thermal, mechanical, chemical, electrical. Let me briefly touch upon these various stress mechanisms. So when we talk about the first stress mechanism, that is particle impact. In a discharge, you have charged particles. These ionized particles will be accelerated by the applied electric field from one end of the discharge to the other end of the discharge. And as a result, these particles can acquire considerable energy. So when those particles impact on the dielectric surface at the ends of the discharge channels, there might be degradation. What degradation do I talk about? There might be local molecular changes. It might break the bonds that are present at the walls. Whatever molecules you have, those molecules may be broken due to bond scission. There may be electrons which are released. But remember, if the dielectric is to be damaged significantly by particle impact, we are looking at very high energies. To cause substantial damage, we would need considerably high energies. And it is really not feasible that just by particle impact, you would really see a significant amount of damage on the walls. So here are some of the chemical bonds and what are the energies that are required for such bond scissions. For example, CH requires 435, CC requires 347, CO requires 729. So you would really need electron energies in excess of 500 eV. The particles should have that amount of energy to be able to cause any significant damage. Of course, it also depends upon the surface situation. What is the condition of the surface? But this is how particle impact can cause damage to the surrounding insulation. Then you can have thermal stresses because you have particles flowing, charged particles flowing. It is essentially current that is flowing. So you have I-square losses. So you have heat being dissipated. When that heat is dissipated in a gaseous environment, the temperature rises. There might be exothermic reactions happening because of the partial discharge. Gas molecules may migrate from hotter regions to lower regions. The surrounding material may undergo chemical reactions because of high temperatures. Essentially, when we talk about thermal stress causing problem in solid dielectrics, we are talking about polymeric materials. Only in case of polymeric materials, the thermal stresses would be able to cause sufficient damage. In other kinds of materials, let's say ceramics, you don't really accept the thermal energies to be, the amount of thermal energies that you have are not going to really make any difference. So these are some of the chains that might be broken due to thermal energies, thermal stresses. Depolymerization may occur, so that polymeric chains might break down and you would start with a certain polymer and you will end up with a degraded polymer. Mechanical stresses might also be generated. In the discharge, there are charges, and these charges migrate from one point to another. And when they travel from one point to another, solid dielectrics have the property to be able to trap charges. What we mean by trap charges, we will discuss, I think, day after tomorrow. When I say trap charges, let us imagine that the solid dielectric is able to hold on to the charges and the charges are not free to move from one point to another. So when you have such charges embedded in the dielectric, these charges would also cause a certain applied field. So over and above the applied field, which is external to the material, you might have superimposed a space charge field. So remember, in an electric field, you have applied an electric field, you have applied a potential difference across 2 points, you have an applied field. On top of that, if you have let's say you have a point charge somewhere, the result would be that point charge would exert a second electric field, and therefore in the vicinity of that charge, you would have the combination of 2 electric fields. So that is what I'm talking about. When you have trap charges, the trap charges will result in a second electric field being superimposed on the applied electric field. And those high electric fields can cause a lot of problem. There might be vibrational mechanical stresses. There might be attractive and repulsive forces between the particles, which may cause the surfaces to be attracted. There might be larger particles, not trap particles, I'm talking about the particles in the discharges, larger particles may be able to impact and actually erode the surrounding dielectric material. They may have sufficient energy to erode material from the neighboring dielectric surfaces. And of course, chemical changes can also happen. Now, of course, it is you might want to imagine that because of high particle impact, there might be small fractures being produced, small cracks being produced in the dielectric material. It is possible, but it is unlikely. The stresses that we are talking about in a partial discharge are unlikely to cause fracture, but that is not impossible. Then, of course, you can have chemical stresses. Whenever you have particle impact, you have thermal energy being released, you have mechanical stresses. All this can result in chemical structural changes. And as a result, you may release species which were not there to start with. And these species may now begin to interact with the dielectric material. So if you introduce new species into the discharge channel, these species will now react with the chemical structure of the dielectric outside, which we did not have to start with, and that can cause further chemical stresses. So for example, these species can be charged species, can be positively charged species or negatively charged species, and some of these species can be highly reactive. For example, ozone. Ozone is a strong oxidizing agent, and then there are oxides of nitrogen. Oxides of nitrogen can interact with air and water and can form nitric acid. And we all know that nitric acid is not a nice thing to have around you. So these are the various stress mechanisms that can happen due to partial discharges. So this is what I mean. So you have partial discharges happening, and as these partial discharges go on over a long period of time, you have chemical species being generated, you have heat being generated, you have molecular abrasion, you have mechanical erosion. All these processes over a long period of time, and here this is very crucial, this is a long-term breakdown process, but what partial discharges can do is, over a long period of time, partial discharges can continue to happen within the insulation, and over a long period of time, it can result in catastrophic breakdown, in catastrophic failure. So partial discharges in themselves are not, in themselves, you often don't care. And you may rest assured that if you have an insulation in service, partial discharges are definitely happening within the insulation. It is not always a cause for immediate worry, but over a long period of time, as the material ages, partial discharges can reduce the lifetime of your insulation in power apparatus. Then we talk about the most important factor, that is electrical stress. You are talking about discharges, which means you're talking about a lot of charges moving around, and then these charges are getting deposited. So remember, what partial discharge does is, partial discharge actually reorganizes the charges. It transfers charges from one point to another. And as a result, all these charges, as I said, over and above the applied electric field, you would have a second charge field due to all these charges which are involved in the discharge. These charges get deposited at certain points, they are reorganized, they get deposited in different other places, and as a result, local field enhancement will occur. So not only would you have degradation, local degradation, which can be of microscopic nature and ultimately can also become macroscopic in nature, you can also have a situation where you have local field enhancement. And as local field enhancement happens, local field enhancement is always a problem and gives rise to many other physical processes. I am going to talk here about one of the mechanisms that local field enhancement can cause, and that is electrical treeing. The reason that I'm talking about electrical treeing is that electrical treeing is one of the, so as I just now said, partial discharges over a long period of time can lead to breakdown, can lead to catastrophic failure. And one of the pathways by which partial discharges can lead to catastrophic failure over a long period of time, and here I'm talking about years, is through electrical treeing. What do I mean by electrical treeing? What happens is, because of maybe existing defects in the material, or because of any reason, if there is local field enhancement, we can have what is called tree initiation. And then after we have the initiation of a tree can progress through the volume of the dielectric material. What is tree? What is electrical tree? Electrical trees are erosion channels. So within the volume of the dielectric, you will have local channels which are produced, and within these channels the material is eroded. So essentially you will have formation of channels which no longer contain the dielectric material, but instead contains air or gas or some other thing. And these channels are they are kind of branched filamentary channels. This is not a very nice picture. Let me try and show you. I don't think I have a very good picture here. I'll show you a video right away. So this is under the microscope, a picture of an electrical tree. And if you can see, there are lots of branches. And because it looks like an upturned tree in nature, that is why these are called trees. Because these damaged structures visually look like the trees in nature, that is the reason that they are called electric trees, because they are driven by electric fields. So what happens is, these kind of trees are produced, and these trees, over a long period of time, these trees continue to progress through the dielectric. And what we know is that, see, this is the same electric tree. This is a picture that I have taken from Desado's paper. We also have certain trees in our lab, but I've not included any of these pictures. Maybe we can show them to you later. So you see, this is the situation that you have at one point of time. And if you continue to monitor the tree, this is the structure that it ultimately takes. So the treeing continues to progress by step addition of branches. More and more branches are added. These branches progress towards the other electrode. And ultimately, you will have a situation where the tree progresses to the other electrode. And you might have a situation that one of these branches will reach the other electrode. And through that branch, there will be the formation of a complete path bridging the two electrodes, and complete short circuit will happen. Now, what I want to talk to you here, because we are not talking about treeing essentially, but what we need to understand, that how do these trees propagate? How do these branches increase? How do these branches grow? And that happens because once these erosion channels are created, within the tree channels, partial discharge activity takes place. So you have PD taking place within these tubules. And because of the stress mechanisms that I have just talked to you about, because of the stress mechanisms, there is damage accumulating within the tree tubules and beyond the tree tubules, so that the tree tubules grow in size and more tree tubules are formed. Now, what I'm going to do is, in our laboratory, we were able to observe this PD happening in tree channels, and we could actually see these tree channels growing in size. These tree channels growing in size because of PD activity taking place. Kingshuk, you will have to ask these people to stop hammering.
Yes, ma'am. We've sent someone.
Right now, I am going to stop sharing my slides, and Asha will show you one of the videos that we have in our lab. First, let us show the video once, and then I will explain to you what it shows.
Ma'am, shall I start the video?
No, I'll just explain a minute. So what we see here is, we see light emission from within the tree channels. What we did was, we produced a large void. Now, through the research that we have done in our laboratory, we are aware that if you have a void, you have a needle plate geometry, and if just below the needle you have a large void, if you're able to incorporate a large void, the void has the tendency to stop tree propagation. So any void that you have in the vicinity of a tree, the tree will tend to progress towards the void, and it will progress to the void, and the void will kind of stop the tree from growing further. Now, this was an advantage in our experiments because since the tree was growing to the void, the tree did not progress beyond the void. I'm talking about a very large void here, and therefore we did not have breakdown. So we were able to observe the PD activity within the tree channels coming to the void, and we can actually see electroluminescence happening. And wherever electroluminescence happens, the tree channels grows in size. Yes, Asha, you can start now.
Okay, ma'am.
So this is the large void that I talked to you about, and you can see electroluminescence happening. And if you observe closely, you can see that the tree channel, originally you had a tree filamentary tree channel like this, but this tree channel is now growing in size. It is becoming thicker and thicker. And wherever the electroluminescence happens, that is the region which grows thicker. So this has become pretty thick. Now, this narrow region is supporting the PD. The PD is happening here. I mean, PD might be happening elsewhere also, but there is a large discharge activity that we can observe because of its light emission here. Now, I don't know if you can see it. It has traveled to this point, and ultimately it will travel towards the void. Yeah, so this is a very nice video that I like to show in my lectures on PD, because here we actually see a filamentary tree channel supporting PD activity, and the PD activity causes stress mechanisms to degrade the insulation around it, and a very thick tree channel is caused. In the very same manner, can you just go back to the just the last thing where you have, so once you have a situation like this, just imagine this is not the void, it is the other electrode. So if you have a filamentary channel which has reached the other electrode, and then what would happen is over time, this filamentary channel bridging the two electrodes through partial discharge activity would grow thicker and thicker and continuous, so that it would be able to support a continuous flow of current from one electrode to the other, and catastrophic failure would happen. Thank you, Asha. Just let me make sure I have the current correct slide. Give me a minute, please. Right. I have here a question from Nilesh Lokhande, but it is not really related to the theoretical understanding, so I'll take it later. Can you see my slides? Kinshuk?
Not yet, ma'am.
No? Something is going wrong here. I'm probably sharing the wrong. Now?
Yeah, because
Okay. Okay, so this is what I meant about the various various stresses that you have in partial discharges. Now, what we need to understand is that when partial discharges causes problems, is it because of particle impact? Is it because of thermal stresses? Is it because of mechanical stresses? I don't think so. What really happens is all these different stress mechanisms kind of come together and drive each other. Let me try to give you an example. Let's say you have heat production. When heat production happens, maybe let's say you have a chemical reaction happening. So you have a chemical stresses. So certain chemical reactions happen. Let us imagine that these chemical reactions are exothermic in nature. As a result, more heat is generated. When heat is generated, maybe there is considerable erosion of the channel. So what I'm trying to say is that one kind of stress drives another kind of stress, and together there is a synergistic interaction of all these stresses together, which results in the material degradation. There is no way for you to be able to predict the exact nature of the stress pathway, the exact pathway through which degradation would happen, and what would be the exact combination of stresses at any discharging surface. But there would certainly be a unique and unpredictable combination of stresses which are present at any discharging surface and which results in breakdown. The synergistic nature of discharge degradation is what we have to take into account. Even remember, I say that mechanical stresses are unlikely to cause significant problems. You are not likely to have a crack. It is true if you only had mechanical stresses in question, but a combination of mechanical and thermal stresses or a mechanical and chemical stresses can lead to the formation of cracks within insulation. So we really need to understand that when various stress mechanisms involved in PG come together, anything can happen, many things can happen. So the synergistic nature of discharge degradation mechanisms cannot be overstressed. That one form of stressing does not in itself result in degradation does not mean that it can be dismissed as a contributory mechanism. So most of these in long-term failures, these contributory mechanisms are what we have to look at and which we need to retard. Of course, what kind of process will happen depends upon the materials that are involved, the local environmental conditions, the field conditions. Many things will just determine what happens, and we have to be aware that we are looking at a very unpredictable and stochastic mechanism. Now, I would like to talk about partial discharge mechanisms, measurements. I am not going to talk about the very many different kinds of measurement techniques that we have in hand. Later in the day, we will have several other speakers speaking about some of these. I will spend some time on the conventional electrical methods. And then I may briefly touch. Yeah. Let me continue. So first I'm going to talk about the partial discharge measurement. Now, actually we have electrical as well as non-electrical methods of partial discharge measurement. And when we talk of electrical measurements, we are not necessarily talking about a single technique. There are several techniques. We might be wanting to measure the individual discharge pulse. We might be wanting to measure the total integrated loss due to PD. We might be wanting to measure the electromagnetic field due to PD activity. Imagine you have a discharge. Whenever you have a discharge, when you have a current, there is of course electromagnetic radiation because of the current. And it is possible to detect this by using trying to detect the electric magnetic field. But I'm not going to talk about that. I am going to talk about the conventional electrical method only. So this is, let us imagine that this is the schematic which shows a void. You have CC. I use a circuit diagram. I use an equivalent circuit to represent the situation that I have. I have the capacitance CC, which is the capacitance of the void, let us say, and CB is the capacitance of the dielectric material in series with the void. And CA is the capacitance of the remaining dielectric material, which I assume does not have any void, so it is in parallel to the void. So this is a kind of very idealized representation. We worked with a representation like this. It is a very ideal representation of the situation. Now, what you would have is, you can imagine the discharge to be a closing of a switch S. So as long as the switch S is open, you just have three capacitances. You have a voltage across the capacitor CA, and CA, CB, CC continue to get charge. At the point, so at the instant when the discharge happens, you have the switch closed. So you have a current IC, which will discharge the capacitor CC. So you have a current ICT, which will discharge the capacitor CC. RC can be considered to be equivalent resistance, which kind of determines the time period of the PD pulse. So if CB can be assumed to be, of course, a combination of CB dashed, which is in series on the top of the void, and CB double dashed, which is again in series, but at the bottom of the void. So CB is the total lump capacitance that we consider in the circuit. And you have a voltage VC across the void. This voltage VC is allowed to build up across the void at the point of discharge. Let us imagine VC is the voltage, and a current IC flows through this closed loop. The resistor RC simulates the time period. Now you have to understand, this is what is happening within the material. I can build an equivalent circuit. I can try to understand it using the equivalent circuit, but I do not have access to any of these parameters. And therefore, there is no way I can measure ICT. I would dearly love to measure ICT. If I measure IC, I would be able to figure out everything I need to know about the discharge. But there is no way I have access to this. This current IC will have a shape which will be determined entirely by the gas discharge process. So depending upon the gas discharge process, various kinds of mechanisms can take place, and therefore the shape can change. I will not go into that, but rest assured that the duration of the pulse would be in the nanosecond range. So if there is a pulse, if there is a current pulse IC when the switch is closed, this will result in the dissipation of the charge which you have built up across the capacitor, a void capacitor over this time, and therefore would also result in a drop in the voltage across the capacitor. Let us imagine that the voltage across the capacitor is change in the voltage across the capacitor is delta VC, in which case the charge that causes this voltage difference can be approximately estimated as delta QC, which is equal to CC delta VC. So the voltage drop that you see across the capacitor, across the void, is related to the charge across the void, which is involved in the discharge. Now, if you have a voltage drop delta VC, you would have a corresponding drop of voltage across the entire test specimen. Remember the metallic electrodes that we talked about? The entire metallic electrodes, let's say the total voltage across the metallic electrodes is VA. I think I show it here. Okay, let us imagine VS is the supply voltage, and let us imagine that VA is the potential difference across the total dielectric, that is CA. So therefore, any difference, any potential difference, potential change, delta VC, would be related to a corresponding change, delta VA. And you can approximately establish a relationship between delta VA and delta VC. And why are we doing that? This is a quantity that can be measured. We cannot measure VC, but we certainly can measure VA. And if delta VA could be measured in an indirect way, it would be related to the quantity ICT And it would also be related to the shape of ICT. Now remember, even though this delta VC is very small, even though the change in voltage is very small, the discharge is caused at very high fields. And we have another problem, which is that we might be able to theoretically relate delta VC to delta VA, and we may be able to measure delta VA. We do not know this CBCA. There is no way we can measure CBCA. And in general, CB by CA would be very small, and I don't think we would be able to measure anything meaningful. So a direct detection of this voltage step by a measurement of the whole input voltage, even if theoretically possible, is not really going to work. Let me recap what I just said. Whenever there is a potential drop across the voids when the void discharges, this can be related in terms of the charge across the void, in terms of the current across the void, to the potential, to a corresponding potential drop across the entire test specimen. Theoretically, this is possible, but in reality, this is not going to be possible. We can measure the potential difference across the test specimen, but we cannot establish the relation between delta VA and delta VC, because we do not know CB, CSCB, CS, etc. And also because we would end up with a very small quantity of small quantities to be measured, which may not be measurable. And therefore, a direct detection of this voltage step by a measurement of the whole input voltage would be a tedious task. And therefore, what we do is we introduce the concept of apparent charge. Now, let us imagine that you have an impedance Z. This impedance Z is between the supply and the coupling capacitor. I remember there was a question in yesterday's lab, I think it was yesterday's lab class, about what is the necessity for the coupling capacitor. What you see here is this supply voltage charges the coupling capacitor. Now you can imagine that the Z impedance kind of isolates CK from the supply voltage. As a result, at the instant of discharge, it is the coupling capacitor which will be supplying the discharge pulse to the test specimen, to the void, to the test specimen. So the CK then behaves like a stable voltage source. The partial discharge takes place over a very short period of time. And for that short period of time, CK is quite, it is a quite stable source. And this is the source which releases the charge. So imagine whenever the discharge takes place, to replenish the voltage drop, you would need to draw extra current, you would need to replenish the charge across the void. The void is self-restoring. So once the charge is dissipated, the voltage goes down to 0, and the charge regains the void regains its dielectric property, and it again allows charge to build up across it. That charge has to come from the coupling capacitor. So CK will therefore release a current IC, and because of that, that amount of charge that CK loses will have to be replenished from the source after the discharge takes place. Now, if CK is much greater than CT, which is generally the case, this can be completely compensated, and the charge transfer can be written as Q equal to integration of IT being the current that is flowing in the circuit, is equal to CA plus CB into delta VA being the potential drop across CA, and that can be approximately written as CB into delta VC. So the charge that I am drawing from the supply to replenish the charge that is lost by the coupling capacitor can be approximately estimated as CB into delta VC. Now, this charge was lost by the coupling capacitor because of the PD taking place within the test specimen. So in a way, this charge is related. This is the charge which is drawn in the external circuit. It is not the charge which is involved in the discharge. But in a way, this charge is being taken from the external circuit because of charge mechanisms within the test specimen. And therefore, this charge is considered to be an indirect measure of the charge involved in the discharge activity. However, it is very important to understand that this is not the real quantity of charge that is involved in the discharge. It is only a charge which is drawn from the supply in response to a certain quantity of charge being involved in the discharge activity. And that is why we need to distinguish it from the actual charge by calling it the apparent charge. The word apparent was introduced because this charge is not equal to the amount of charge locally involved at the site of discharge or cavity. This is very important. Then what is this charge? We have a definition for this apparent charge. Apparent charge Q of a PD pulse is that unipolar charge which, if injected within a very short time between the terminals of the test object in a specified test circuit, would give the same reading on the measuring instrument as the PD current pulse itself. So if you had a certain quantity of charge involved in the PD, you would be able to see a certain quantity of charge being observable across the terminals of the test object. So therefore, we define apparent charge as that quantity of charge which, if I inject within the test if I inject across the test terminals, will give me the same reading as what the PD charge does. This Q and that Q are not same. The apparent charge is not equal to the amount of charge locally involved at the site of discharge, and that charge cannot be measured directly. So what is the relation between the apparent charge and the real PD charge? The relation is that both have the same effect on the measuring instrument. If a certain PD activity takes place, you read 2 on the measuring instrument. That corresponds to a certain quantity of charge which is not equal to 2, which when injected across the test object terminals will also give you the same reading 2. So this is very important to understand. The apparent charge is a unipolar charge which is injected within a very short time between the terminals of the test object and gives the same reading as the PD current pulse itself. Apparent charge is, of course, expressed in picocoulombs. So we measure PD discharge activity in picocoulombs. So this is what we do. This is the schematic of a circuit. As you can see, there will actually be, apart from this discharge current, there will also be 2 other currents which are flowing in the circuit. There will be a current IK and there will be a current IT, which is being drawn from the supply. IT is the dissipation current in the test object, displacement current in the test object, and IK is the displacement, primarily the displacement current in the coupling capacitor. These currents will also be there. And in addition to that, at the instant of discharge, there will be a current IT flowing, not from the supply, but in this loop. And this current IT will be measured. It will have to be amplified. And that is the current that you can observe in your oscilloscope. It will have very small magnitude, 10 to the power minus 4 amperes maybe, and it is of nanosecond duration. So you will have to figure out ways of being able to detect and sense the circuit. Also, since this is an impulse event, it will depend upon the bandwidth of your measuring equipment, what you measure. Now, this is the basic idea behind PD measurement, and this is generally called the straight detection circuit. The problem with straight PD detection circuit is that if you have any other current flowing for any reason, it will interfere with a very small current that you're trying to measure. And therefore, the signal to noise ratio in straight detection circuits can be prohibitive. So if you have any kind of discharge within this entire circuit, for example, when we have the coupling capacitor, we have to make sure that it in itself is PD free. Even the source can be a problematic source of noise. And therefore, if you want to use a straight detection circuit, you will find that there is a lot of screening, there is a lot of filtering, and even then you might not be able to obtain measurable quantities. And therefore, and also remember, in fact, whenever we switch on suppose we're trying to measure PD in the lab, even in the lab environments, very often, as soon as we switch on the PD detector, what we see is we see a lot of PD pulses straight away. I mean, the moment we start applying voltage, we start seeing a lot of PD pulses. And immediately we know from experience that this is not PD that is happening, but maybe there is a sharp corner somewhere, there is dust somewhere, which is leading to a lot of corona. And not even PD, just corona happening. And we need to get rid of that. So therefore, the strain detection circuit is not really very amenable to any kind of measurement, and it is difficult to avoid partial discharges in the leads themselves. So therefore, there is a basic improvement of the strain detection circuit, which has been in place right from the outset, and this is a balanced circuit. As you can imagine, it is very similar to a sharing bridge. As you can imagine, it may be difficult to measure a small quantity when there is a large current flowing through the circuit. But if you can set up a bridge circuit so that when you do not have a PD, there is no current flowing, or there are very small noise currents which can be filtered out. And in that scenario, even a small PD pulse amplified properly can be measured. So the coupling capacitor CK and the test specimen CT are taken to form the high voltage arm of a bridge. And the low voltage arms are basically similar to the sharing bridge. The bridge is adjusted for balance. And in this scenario, when a discharge pulse happens, it can be more easily measured. Now, of course, if you want to have balance with two capacitances, the best way to fulfill this condition is to have the same dielectric media in both the cases. That may not always be possible because the test specimen may change, but you can try and do that. So it is, and of course, the coupling capacitor, as I already mentioned, has to be discharge free. Otherwise, what are you measuring? So this is about the basic circuits for electrical PD measurement. Now, once you are able to measure PD, what do you do? Do you just take the single pulses and try to do something with that? Maybe not, because that's not going to give you much information. In fact, those of you who have done any kind of research in PD, you might realize already that PD measurement is not a problem. We now have various techniques available to us which can measure PD for PD measurement. The problem or the challenge is in analyzing the data that we measure. How do we make sense of the data that we have? We can acquire large quantities of data. In fact, I know that many students who work with PD have at their disposal a large quantity of data, and then they do not know what to do with it. So PD analysis is what is very challenging. How do you make sense of the data? Now, of course, I'm not going to talk about those things. I'm going to talk about something very basic. How do you measure PD? What we measure PD is not the individual pulse, but what is the discharge pattern. Now, what do I mean by the discharge pattern? By the discharge pattern, I mean the phi QN pattern. If you look at this figure, which I have drawn in 3D, of course, you can use phi QN patterns in 3 dimensions with 3 axes, or you can also take a 2-dimensional picture, just 2 plots instead of 1. So what you do is, there are 3 things that we are interested in: phi, Q, and N. I'll start with Q. Q is, of course, the charge quantity. A discharge is measured by the apparent charge. So when I say I have a large discharge, I mean that it is of 5 picocoulombs or 20 picocoulombs or 500 picocoulombs. I measure it in units of charge. So what is the magnitude of the discharge? That is given by Q. Next, I have phi. Phi is the phase. When I apply a AC voltage, at which phase of that AC cycle does the discharge occur? This is important information. And lastly, we have N. What are the number of discharges that you would have? Remember, as I said, PD is pulsative in nature. So over one single cycle, you will have a large number of PD pulses. And because it is stochastic, this the number of PD pulses will also not be consistent. I mean, not be constant. So the phi QN pattern gives you the information that you have N number of pulses of Q magnitude at phase phi. and you have another n number of pulses of another magnitude q1 at phase phi1. And what you do is you let this information accumulate over a large number of cycles so that you build a pattern which is discernible, which you can identify. You can build up identifiable patterns. Now, when I say, so if you look at this figure, what you have here is you have the number n on this axis, you have the phase in the inward axis, and you have charge on the x-axis. So charge on the x-axis, n on the y-axis, and phase phi. You see a kind of two twin towers. So depending upon, this is the phi qn pattern, and most known defects have discernible and identifiable patterns. I have here a picture. This is not in 3D, but in 2D. I have a picture from a paper. These are the PT phase patterns that you see in various shapes of cavities. You have perspex dielectric material, you have a square cavity, you have a flat cavity, and you have a narrow cavity. And as you let the phi qn pattern build up over a large number of cycles, you can see that the patterns are completely different. So maybe if you were experienced and if you were living in an ideal world, just by looking at this pattern, you would be able to say, oh, you know, this is a cylindrical cavity. Let's look for a cylindrical cavity. Do you really think a cylindrical cavity? I mean, we don't have a cylindrical cavity here. Let's say a narrow cavity. A narrow cavity. And is a narrow cavity, if a narrow cavity is expected, where do you expect a narrow cavity to happen? And if this narrow cavity is a delamination, then we have a problem, we have to take action. But if it is a flat cavity, it is somewhere in the middle, we don't care. So you can take action depending upon the pattern. In an ideal world, this would happen in the sense that you would be able to build up the phi qn pattern, and the phi qn pattern would give you an indication of the nature of the defect and what course of action is indicated. So when I say that you have to build up this pattern over a large number of cycles, what remains unsaid is that over these many cycles, so I'm probably talking about 500 cycles. So over 500 cycles, I let the phi qn pattern accumulate so that I have a nice discernible pattern. This is important so that you don't have stochastic variations. But at the same time, you need to remember that to build up a phi qn pattern properly over a large number of cycles, the PD pattern has to remain the same over those large number of cycles. So larger the number of cycles that you involve in your computation, in your measurement, more statistically accurate will be your measurement. More statistically accurate is your estimation. But if you keep the voltage on for a very long time, it is always possible that the PD swinging into action, starts exerting its own stresses and causes changes the PD pattern. The PD, either whatever is a problem changes and you start having a different kind of PD, or the PD in itself changes the situation. For example, the video I showed you, we are not going to get the same PD when the PD is through the filamentary channels, and then when suddenly the PD causes the channels to become thicker, and there in that scenario, we had many-fold increase in PD pattern, in the PD magnitude. So the PD magnitude is not, PD pattern is not going to remain the same if the stress mechanism comes into action or the PD, more and more other PDs begin to happen. But if that does not happen, you can build up such patterns. And what you would really do is you would build up a database of such signatures. And based on that database, you should be able to, or you hope to be able to detect the PD and decide what course of action to be taken. Now, as I have already been mentioning, there are various measurement issues involved with electrical PD. External interference is a huge problem. We need to use inline filters. When you talk about these nice looking PD patterns, you're assuming that there is only one source of PD. But in real insulation, you would have various sources of PD. You would have various types of PD happening. And all these signatures will superimpose on each other. And so potentially there would be a large number and type of discharging sites present. And the characteristic patterns associated with this specific discharge conditions will be swamped out. Also, okay, such and such PD is happening. Will that give me a problem? Do you really have an answer to that? Most of the time, we do not have a specific answers. The information is never linear, and therefore, the information that is there cannot give me a thumb rule for my next course of action, but it can be very useful in assessing insulation integrity. So the measurement methodology would be to measure the magnitude and the reputation rate. Larger magnitudes means you have larger voids. If you have and if you have a larger reputation rate, it can mean many things. It can mean more sites. It can also mean that you have smaller PD, smaller voids, but many of smaller voids. The phase importance is important. To give you an example, apart from the simple phi-QN pattern, there are other questions which can give you the answers to which can be useful. Relative magnitudes of discharges in the positive and negative half cycle. So if you see that you have the same number of pulses in the positive half cycle and the same number of pulses in the negative half cycle, you can figure out whether the discharge is insulation bound, or is it a metallic contact, or is it a metal to metal contact. So once you know what are the kind of materials which are involved in the discharge, you can make an educated guess about the location of the discharge and whether you need to take action. Another thing that can be useful is, does the PD pattern vary with increasing voltage? Suppose you increase the voltage and you do not see any change in the PD pattern. It would probably mean that you have fixed cavity dimensions. The same size of cavities are there, and it simply means that if you increase the voltage, they discharge more often, but that's it. But if you see that there is a variation with the increasing voltage, it might mean that at lower voltages, only certain voids break down. And when you go to higher voltages, some other voids which were able to resist the lower voltage begin to participate in PD. So there are many kinds of things which you need to do, and all this information taken together has to be processed properly to be able to get any meaningful data in real life. So what is generally done is, you look at the trend. You don't look at absolute parameters. You look to see whether the trend is changing. If the trend changes drastically or abruptly, you know that it needs attention, and then you look at what is happening. Ordinarily, what we would do is we'd create lookup tables pertaining to specific conditions. This is where your engineering and scientific judgment comes into play. You have to figure out what kind of PD you expect, and you have to create models of such PD, put them in the lookup table, and then you have to take the PD patterns, you have to analyze them properly for changes in parameter values. Is this PD pattern really different from this second PD pattern, or they just look statistically different? All these things has to be pulse sequence analysis. One important thing is, for example, when we measure, we do PD measurement when we have trees. One important thing that we see is, ordinarily, the PD pulses that you see within trees are not really any way different from a PD pulse happening within a void. So how would I know? Now, when we see that there is a lot of PD activity, and this is followed by an extended period of inactivity, a quiescent period, and then again you have a large amount of PD activity, this is kind of specific to trees. And immediately we know that even though the PD pattern resembles the PD pattern of an internal void, this is not just a void, but this is a tree, because you have this kind of treeing is characterized by bursts of PD activity followed by relatively quiet periods. This is not what you would see in just distinct voids. So there are many things that need to be characterized. And as I said, measurement is the simpler part. More difficult part is, okay, I would like to quickly touch upon calibration. Now, since this is, as you have seen, what we are trying to do is we are trying to characterize the PD happening at a particular site in terms of charge across the test terminals. And apart from that, as in all equipment, we need to calibrate, and this is especially true because the PD pulse is an impulse event. An impulse event means it carries all kinds of frequencies. Now, depending upon which frequency you are measuring at, you would have different contents of this. You would be able to detect different contents of discharge energy. And therefore, depending upon which bandwidth you are measuring, depending upon your setup, calibration is very important. And what we do, you will see this later in the afternoon session. We first use a calibration pulse for calibration. What is a calibration pulse? The calibration pulse is a discharge simulation pulse of known magnitude, which is injected into the detector at the point where the real discharge pulse enters the detector. So across the detector, we inject a pulse of known magnitude, which is expected to be similar to the discharge event. And then we see what do we measure at the detector. Remember, the detected magnitude is a function of the injected, so you have to have a pulse of the same nature, but it is also a function of the bandwidth of the detector. The other thing is it is also a measure, it is also dependent on the path. So what we are trying to do is we are trying to simulate the same path that the PD would take, but of course we don't exactly do it. And then we have to look at the bandwidth of the detector. When I talk about PD parameters, what are the PD parameters that I'm talking about? There can be several PD parameters that can be of interest. One could be discharge energy, where P is charge into voltage, the discharge inception voltage. Now, when you apply voltage to a test specimen, initially you will not see any PD. So you can keep on increasing the voltage, which increases the field across the void. As the voltage increases at a certain minimum voltage, you will start to see a stable PD pulse, at least one single stable. It's not that a PD pulse comes and goes, a PD pulse which is there to stay. When that happens, that is called the discharge inception voltage. Now, when you increase the voltage further, the PD pattern will change. You may have more PDs per cycle, you may have larger PDs, etc., etc. All these things will happen. Now, when you keep reducing the voltage again, the steps should be to a certain extent retraceable, and then there will be a certain voltage. When you go beyond that, below that voltage, there will be no PD available, no PD observable. That is called the discharge extinction voltage. Now, you would ordinarily expect that the discharge inception voltage would be equal to the discharge extinction voltage, but that is not necessarily true. We often see that VI is much greater than VE, and that is because the energy that is required to cause the PD to incept, that is generally higher, whereas the energy required to keep something, a PD is already there, just to keep it going, you might need lower voltages, and therefore it might be that the voltage extinction voltage is less than the inception voltage. You might measure the discharge current. I is equal to summation Qi by T. That is your total charge. Discharge power, which can be measured as I square T. Discharge intensity, the total number of discharges N in time T. Here, I'm not talking about N in a particular phase, but over a particular time T, how many discharges do you see? That is measured as discharge intensity, quadratic rate. So there are various parameters that can be measured and can give us useful information. When I was talking about calibration, I told you that calibration depends upon the injected pulse. So you have to inject a pulse of typical nature. It depends upon the bandwidth because you have to decide which frequencies you are measuring. And apart from the bandwidth, there is also the issue of path. So the PD pulse may have to travel a large distance before it reaches the detector. And as it travels through a large insulation, it may suffer attenuation as well as dispersion. Attenuation, its magnitude may be reduced because of the dispersion, the dissipation of energy along its routes. The other thing that I'm talking about is dissipation, in the sense that the PD pulse is an impulse event and it has infinite frequencies. Now, not all frequencies travel with the same velocity through all media, and therefore different frequencies in the same pulse will travel with different velocities. So they will reach the detector at different points of time. So the shape of the pulse that you observe at the detector might be very different from the PD pulse at the point of origin. The propagation path may be complex, composed of inductive, capacitive, resistive components distributed in a nonlinear fashion. Impedance paths are dependent on frequencies. Some frequencies may be lost, some might resonate. So all this will cause a problem. And this is of essentially more concern when we are dealing with large equipment like generators, motors, and transformers, and research in these areas are still on. So to conclude, you have several issues. Narrow band detectors may indicate smaller pulse magnitude. Wide band detect because you are measuring at a frequency where the energy content is low. So go for wide band detector. If you go for wide band detector, you're probably going to allow more noise. So it is very difficult to figure out what will work and what may not work. And that is why what I have been always mentioning, trend analysis is more important than absolute magnitude. If no matter whatever problems you're facing, if you see a sudden change in the trend, in the PD pattern, a gross change, it definitely means something is going on. So you would have to use certain noise elimination techniques. You can use software, you can use hardware, you can use, in fact, increasingly people use neural networks and wavelet analysis. I'm not going to talk about that. In conclusion, okay, before I finish, I still have some time. I'll just briefly touch upon the fact that because electrical PD measurement techniques have such a lot of problem, we have evolved very many other techniques. And in doing that, what we realized is whatever discharge is dissipated in a PD could also be detected. So if you have sound being emanated, you can try and detect sound, and detection through sound will help you detect and locate a PD. And therefore, we have a lot of literature and even commercial use of acoustic PD detection techniques. And acoustic PD detection techniques have a better look. So it's not always enough to just be able to detect that PD is happening. We also need to be able to locate the location of the PD. And in doing that, acoustic PD detection is important. Then you have chemical methods where the chemical changes that the dielectric material undergoes due to PD, due to the combined effect of PD happening over a long period of time, can give you a measure of the PD activity. And this will be touched upon in the afternoon. Then you can have UHF techniques where you measure not in the range of you measure at ultra high frequencies because the noise pollution at those levels are low. Then you can have light emission. Of course, light emission works only good in over open systems, or you can use thermal cameras. Thermal cameras is for thermal emission, or daylight corona. So there are various other non-electrical techniques. And what we increasingly do is we have from experience some idea about which technique is suitable for which purpose. Generally, we would use a combination of electrical and a non-electrical technique to detect and identify a PD with reliability. And depending upon which power apparatus you are targeting, you would choose your PD detection techniques. There is no thumb rule for that, but your engineering judgment and your physical understanding will help you make that decision. In conclusions, as I say, PD studies have a twofold importance. It enables the development of new insulating systems which are resistant to PD stressing. For example, in our lab, we work with nanodielectrics, and we have seen that certain nanodielectrics are able to resist erosion due to discharges on its surface. So if we expect a material to be used where we know that there will be a lot of PD happening or a lot of tracking happening, we would choose a material. We might try to use a nanodielectric instead of an ordinary polymer. Also, it's not always possible to kind of replace every material with a material that we like. But even when we cannot do that, if we do PD monitoring, we might be able to predict the remnant life for existing plant systems. So therefore, for both these things, to prevent PD and to monitor PD, we have to have reliable strategies to gain benefit from that. We have actually come a long way. There is a large body of literature on PD measurements, PD analysis, etc. But we still are faced with certain challenges. We don't still have a thorough understanding of how PD causes degradation. If we knew that, it would be easier for us to estimate what course of action to take. And what are the key parameters of measurement? What should I measure to be able to get a proper estimate of how serious the PD condition is? And maybe a simpler problem is the ability to make measurements under adverse conditions. For example, in case of rotating machines, where you have, or even in large power transformers, where you have large materials which are kind of opaque to maybe acoustic waves, or even electrical propagation is noisy. So it is difficult to make measurements. So we are still looking at these challenges. And once we do that, we will have done a lot. But even without getting there, PD measurement techniques are very important and crucial to condition monitoring and understanding of how dielectrics behave. Thank you. These are my references.
Thanks, ma'am, for a very detailed understanding of the physics and the electrical measurements of partial discharge. Now we will look to the questions that has been asked throughout the course.
Okay. I will take the first question later. I'll take the second question. You can unmute.
Ma'am, you have to make me host or.
Yeah. Oh, I have to. Yeah, I've done that.
Okay. Second question is Sheikh Mohammed Tayeb. Yeah, you can ask the question.
Hello, ma'am.
Yes.
Ma'am, actually, in that PD pulse that you showed, that when the ratio of EA and EB means as the ratio increases, the number of PD pulses is increasing.
Right.
So I wanted to know that in that example that you showed that 4 PD pulses, means, is there any specific reason about means how the shape of the PD pulse is coming? Because in one of the pulses you showed that it is following the applied sinusoidal voltage, and in the negative pulses that you showed, it was not following the.
Oh, no. That is a schematic measurement. That is a schematic diagram. That doesn't show the PD pulse. It just shows the instant at which the breakdown happens. So you have to understand that you're not really going to have PD pulses which last half cycle. That's not going to happen. The PD pulse is of nanosecond duration, and it is, if you actually superimpose the PD pulse on the sinusoidal wave, you'll just see impulse events. And the actual PD pulse shape will depend upon your measuring equipment. And it is typically, we have measured it using electrical techniques. We have measured it using acoustic techniques. It is a kind of impulse event of nanosecond duration.
Okay, thank you.
That was Shomodeep, right?
Yes, ma'am.
Sheikh Mohammed is raising his hand.
Yeah, you can talk. You can unmute yourself and ask the question.
If you have a problem, then maybe
you can try.
Okay, so I'll just read out the question. He probably has some difficulty. He is asking, apart from voids, free moving particles, what are the different causes for partial discharge? It doesn't have to be a free moving particle. It can be a moving particle. So I would say that it is not really possible to, specify all the possible sources. What you are going to look for is you're going to look for a reason for local field enhancement. So if there is any reason which might cause local field enhancement in a particular region, then definitely that can cause PD. It can be just dust particles. It can be manufacturing defects. It can be existing trees. It can be space charge. So there can be very many reasons for that. But the point is that what we are looking for, so what I had enumerated are the likely reasons that are there already. What are the likely reasons that we see all the time? But that is not a comprehensive list. So anything that can cause local field enhancement will probably give you PD.
Next is Nitin Jha. Okay, he has asked, PD is generated in DC voltage also? If yes, what will be its pattern? And you mentioned like AC in one cycle.
PD is generated in DC voltage also. What will it be its pattern? So that is exactly the reason that I gave you the explanation for the PD pulsative nature of PD. So what will happen in case of DC is you are maintaining a constant voltage. So every time the breakdown strength is exceeded, it will break down and go to zero. And then immediately it will see a reason for the voltage to rise again. There is excess voltage and it will be able to accumulate over a long period of time. That is the point with DC voltage. Over a long period of time, charge continues to accumulate across the void. So how much time it will take to accumulate and when the PD pattern will happen, it is very difficult to foretell, which is why I'm not using the example of DC voltage to explain the nature of the PD pulses. It will depend upon the way the charges accumulate across the voids, and there are various processes which contribute to that mechanism. Nitin Jha has another question.
Yeah.
If oil has more particle counts, then is there a possibility of having PD in oil? Yes, I am not going to elaborate on the particle behavior in more detail. I would suggest that you look up YouTube. I have a course that I offered in the previous semester. It is called EE634, where I talk about breakdown in liquids. That might be helpful for you. Also, of course, there are lots of textbooks that deal with it. In a transformer oil, you would have a very different PD definitely happens, can happen, and happens in transformer oil. In a transformer oil, PD often happens from particles which are moving around. So as I said, wherever that you have field enhancement. Also, in case of liquids, you have to remember that bubble formation, floating particles, all these things also contribute to the breakdown process. So if you have a PD in one region, it can ultimately lead to breakdown very easily. And yes, so that will kind of contribute to the PD pattern.
Next is Niharika. You can ask the question. Unmute yourself.
I've already asked, yes.
Yeah.
Yes, Niharika.
You can unmute yourself.
No, she's not.
Okay, also, yeah. So how does the migration
read it out?
How does the migration of gas molecules takes place in a solid dielectric as the solid is not free flowing? Does the gas void shift its location or the gas void gets elongated?
No, migration of gas molecules in solid dielectric to a certain extent is possible, but I think that's not what you're asking. Gas formation will happen, but I think that's not what you're asking. You're talking about the gas discharge. When you're talking about the gas discharge within a solid, we are talking about gas discharge happening within a small void. We are talking about gas discharge happening within a small void, which is encapsulated within the solid. And the discharge is localized within that void. But because of the stress mechanisms of the partial discharge, the void can change its shape, can change its structure, it can get elongated. It will not move from one point to another, but it can change its shape, yes.
Then Sheikh Mohammed Tayeb has asked two questions. What is the best diagnosing method for detecting PD?
As I said, there is no best diagnostic method. Find out what you are trying to do. Look at the literature, see which technique has given good results, try and use it in your situation and hope for the best. So you will find in the literature a kind of analysis of what kinds of techniques used for certain scenario. For example, in gas insulate, there are very few instances where I can give you very, cut and dried answers. But one thing I can say is, for example, acoustic diagnostics came into the picture with gas insulated substations, because in gas insulated systems, we do not have access to the interior. And therefore, acoustic works very well with enclosed structures. But then the technology has moved forward. We have various kinds of sensors available, which we can insert. So it's a very dynamic field, and it's very difficult to, I mean, it's impossible to say what is best. But yes, we have in the literature, you'll be able to find that, okay, for transformers, electrical and acoustic combination may work well. For circuit breakers, something else might work well, which I don't remember at the top of my head. But generally, we are looking at imperfect solutions, and we are looking at generally a combination of two or more techniques. Could you please elaborate on ultra high frequency sensor method of detecting PD? That will take one more extra lecture, so you can talk to me beyond this course and we can discuss this. Okay, there is somebody with initials. In thin film treeing will occur, POCO. In thin film treeing will occur because a thin film also has a certain thickness. Treeing can occur. And depending upon the electrode structure, depending upon the field, depending upon the nature of the field, the direction of the field, you'd have to map the field to figure out, I mean, you'd be able to predict to a certain extent in which way the treeing will progress. But yes, in thin film, treeings will occur. What is the difference between the PD pulse and calibration pulse? That is Ritanjali Behera. The difference between PD pulse and calibration pulse, PD pulse is the actual pulse that I want to measure. It is not within my control. I apply a voltage across the test specimen, and when I apply a voltage across the test specimen, a discharge occurs. I do not have any prior information about what would be the nature of the discharge, what would be the magnitude of the discharge. I don't know anything, and that is what I would like to measure. Whereas you said calibration pulse, right? Yes, the calibration pulse is a pulse of known magnitude. It is not a real discharge pulse. It is a synthetic pulse, which I deliberately insert into the test terminal so that I can begin my measurement. When you attend the session this afternoon, probably you will be able to get a better idea of what I'm talking about. Since I'm talking about specifics, let me go up to the first question which I had left, which is from Nilesh Lokhande. How to identify PD mechanical stress over connected cable in system? There is no way you can identify PD mechanical stress in any system except in the laboratory, and that too, it is doubtful. As I said, it is very difficult to figure out if PD is causing a problem, whether it is a mechanical stress which is causing the problem, whether it is electrical stress which is causing the problem. More often than not, it is a combination of various stresses which is causing the problem. And therefore, I do not know of any way or of any need to figure out what is the mechanical stress. But if you're talking about identification of PD in connected cables, there are various techniques available. In fact, there are commercial techniques also available where you have a detector at one end, you inject a pulse at the detector end, the pulse travels through the cable, reaches the fault location and is reflected back, and there will be another which will be transmitted. So by looking at the time ratios of travel of these various pulses, you should be able to locate and detect pulses in a cable system. But then again, that's another story which I'm not covering in this particular lecture. Many times due to stress over connected systems, due nuisance kind of faults occurred, create start of minor degradation. I don't really understand this question. But if you're saying that if you have systems with high over voltages or a lot of connections and there is a lot of stress and there are lots of faults, whether degradation can happen, yes, degradation can happen, PD can happen. I'm not exactly sure what you're asking.
Next is Rohit Shangiani. Are PD pulses reproducible?
Yeah, PD pulses should be reproducible in the sense that you would not get the exact phi-QN pattern, but statistically you should get the same phi-QN pattern over, I mean, even over different measurements. Yes. It is a stochastic process.
In some research papers, it is proved that nanoparticles suppress the space charge. My question is, in the same way, will nanoparticle restrict the PD entry?
Yes, it is possible. Nanoparticles incorporated in polymers, we have done experiments in our lab. We know that treen can be suppressed. We know that PD not necessarily can be suppressed because PD, PD is more of a manufacturing thing. And when you create nano composites in the laboratory, you're not really going to be able to get rid of voids and interfaces. But what we have seen, what I already mentioned, is that when you have material and over on that material PD impinges, that material degrades, and that very often happens in cables, in transformers. You have that scenario where you have some dielectric which is likely to be in the vicinity of discharges, and yes, in that case nanoparticles, nanocomposites have shown ability to resist degradation. Yes.
How do we correlate temperature deviation or variation effect on PD value?
Well, Nilesh, you will have to explain this question to me.
Yeah, Nilesh, you can unmute yourself.
Hello.
Yeah. Yeah.
Many times we observe related to the thermal stress over sometimes let's consider epoxy bushings or insulator when internal contact get overheated. So when it get overheated, there may be some minor cracks internally, which we cannot easily view through our eyes, but it can be possible through microscope.
Yes.
We can able to view, and many times we found some variations at particular 30 degree, let's consider 30 degrees Celsius, it having 10 dB value. When the temperature goes above, because it during a circuit breaker system, it has to withstand that whatever the rated current. When it reaches to the rated current value, then at that particular surrounding bolted joints or something like that, there are some metallic inserts. That surrounding area, we found some minor cracks, and due to which the PD value get increased from the
so I understand
normal
what you're
case
saying.
to 10.
So I understand what you're saying. You're actually talking about the synergistic processes. So you see, when you have high temperatures, you have degradation mechanisms happening. Now, as you say, when you have degradation mechanisms, you have cracks, fissures created. Wherever you have cracks, wherever you have fissures, wherever you have delamination, PD will happen. So what you're talking about is fault degradation of the dielectric due to thermal reasons. And no matter what the reasons, whenever you have degradation mechanisms, that can lead to situations which will cause local field enhancement, and therefore PD will happen. And that there is no thumb rule for that. You will have to just correlate what you're seeing, and you will have to repeat and build PD signatures, and you will have to do the correlation yourself. Yes.
Next, Vaibhav has asked how to distinguish by seeing graph that PD arises from tree or void.
He has one more question before, how one can understand PD location by seeing. Okay, you cannot understand PD location from the PD graph. In fact, this gives me the opportunity to mention one important thing that I missed. The electrical PD detection technique, the conventional electrical PD detection technique, does not give you the opportunity for PD location. So if you want to locate PD, which you actually do most of the time, you need to involve some other non-electrical or other kind of electrical technique. So in fact, that is why you need acoustic, because with electrical PD, conventional PD detection measurement, you might be able to figure out that, okay, there is a PD going on, but you have no clue where it is located. And for that, you will need either maybe acoustic detection technique or UHF technique or very many other techniques. That's one point. How to distinguish by saying graph that PD arises from tree or void? I think this will be discussed in today's afternoon session, but as I already said, when you have partial discharges in trees, what you actually have is you have erosion channels, which means that you have actually internal voids. You have voids within the insulation. But voids can be of various shapes. In tree, you have narrow channels. So there would be a signature pattern which is typical of narrow channels, but from that you will not be able to figure out whether these are isolated voids or these are trees. So in trees, you will have a large number of isolated voids. And as I said, it has been observed, and we have also seen, it is reported in the literature, and we have also observed in the laboratory, that when you have trees, what you will see is, you will see a lot of activity and large PD magnitudes happening, all phases, very busy, and then suddenly everything is quiet. Nothing seems to be happening, but PD probably is on. The tree is there, voltage is on, nothing seems to be happening. And for 1 hour, for 2 hours, nothing happens. And then suddenly you see a lot of trees, a lot of PD activity again. So whenever we see that kind of pattern, we know that their tree is likely. Actually, you see, you have to understand that when you want to detect or locate a tree, you have to bring your physical understanding, you have to bring your engineering judgment into the picture. You have to know what to expect. So there is no real, I don't think you can say, okay, if A, then B. No. It doesn't really happen that way.
How can I relate the impurities present in in-service transformer oil from the PRPD patterns obtained by its PD measurements?
PRPD patterns will not measure impurities. PRPD patterns will only measure any partial discharge that is happening due to this impurity. So if you have
Yeah, who is talking?
Yeah, I have muted him.
Okay.
What was the question I was trying to answer?
Yeah, how can I relate the impurities?
Yes, particles. Yes, sorry, particles. Yeah, particles. The situation is like this. PRPD patterns will not look at the particles at all. Will not observe the particle. When you have a particle in oil, there is local field enhancement around that particle. And if that local field enhancement is high enough to cause a partial discharge, it is only then that we will be able to measure the PRPD. We will see it in the PRPD pattern. And when you look at the PRPD pattern in transformer oil, you will know that it must be through particles or it might be through other reasons. So to figure that out, what you would need to do is you would have to take a control situation where you have a very pure transformer oil, put in 2 particles and see what is the PRPD pattern, put it in the lookup table, then you go to the actual oil. So it's convoluted.
And one final question, generally rod plane configuration is used for experiments due to its low critical electric field. May I know where do we see exact rod plane configuration in real applications?
Where do we see exact rod plane? We see exact nothing in reality. Experiments, rod plane configuration is used because it's an IEC standard. It gives you low critical field. If you had sphere-sphere gap, you would not have any non-uniformity. Rod plane gives you low non-uniformity. But as in any situation, in practice, you would see a situation which can be approximated as a rod plane configuration. Or what you might know is that in this scenario, I have a low critical electric field, and therefore whatever I see in a rod plane configuration is likely to be a good approximation of what I see here. That's the best I can do. I do not understand why this question comes from an anonymous attendee, but that's okay.
Maybe he has not given his name.
Oh, okay. Yeah, while logging in. Okay.
Yeah.
Okay.
So if there is no further question.
Yeah, we are already out of time, really.
Yeah. So thanks, ma'am, for this very insightful outlook on PD.
Thank you. It's been a pleasure. I hope somebody somewhere has benefited from this talk.
Yeah. So our next talk will begin after 10 minutes from 12:30. It will be about partial discharge measurements of instrument transformer by Arijit Basu.